No. I finished it all perfect. Okay, guys, I'm gonna ask that like you don't move stuff around.
Hey, can anyone break a 10? Can you break a 10?
I can.
Oh, you can break a 10?
Okay, Corday. Am I on frame? Huh? Am I on frame?
Barely.
Am I?
Well, you're not gonna be there the whole time. You know what I mean? So go where you are.
Yes, okay. So everyone, we're gonna start now because the period already
Bro,
started.
I'm gonna put it back a little.
Sure. Okay, but fix the position. Okay.
All right. Should be good.
Wait, can I give this thing like a 1 second like?
Okay, so we're gonna start by going over limits, right? So limits are so important that I'm even gonna write the word up here because basically for every single topic in calculus, everything just kind of founds itself on limits. It's the foundation for limits, right? And so say we have a graph like this, right? And then we have here, but then it has a hole over here, and then the graph continues, right? So what the limit is actually looking at whenever you have a function, and say this is the function f of x, right? What the limit is actually looking at is not what the function value at a certain point is, right? So say this were the x a, or x equals a. So if we were to ask ourselves the limit as x approaches a of f of x, well, it actually doesn't matter what the function value at this exact point is going to be. All that we're cared about, or all that we care about, is what the function is approaching, right? What it looks like it's going to do. So at this point over here, say this is y equals 3, right? So the function isn't actually defined at x equals a to be 3, but we see that if you kind of follow along the path of the function, right, we see that it looks like it really wants to equal 3 in the y, right? So we say that the limit as x approaches a, which is this x that we're choosing right there, of that function, that's going to be 3, right? And it doesn't matter what the 3 is, right? The 3 could be like any number. The 3 is just an arbitrary number that I chose here. But just kind of remember, fundamentally, if you're looking at a graph for a limit, we're just caring about what the function looks like it's going to do, right? The function can be defined all the way up here.
Thank you, students and teachers. We appreciate that you're in the classroom getting that study time down. Please make sure they take advantage of this time. It's a great opportunity provided to you by your teachers. Just an FYI, the pizza is on its way. We apologize for that delay.
How much is pizza? The pizza's on its way.
Yeah, $2 a slice.
It's $2 a slice.
Money's in my car.
That's a scam.
Is that it? Okay, I think that's it. Okay, so see, we could have the function value be actually defined like all the way at y say equals 7, right? But we don't care whatsoever what the function value is. We, with the limit, are only concerned with what the function looks like it's going to do, right? So remember that. A limit doesn't care about what the function actually is at a point. It just cares about what it looks like it's going to do. So that was kind of the first method in interpreting limits, right? And so besides graph, we can the AP test can also give you tables. So say they gave you a table that has here, super long table. So say they gave you the x value of 0.9, say they gave you 0.99, 0.999, and then they gave you 1.001, 1.01, 1.1, and over here you have 2.9, 2.99, 2.999, 3.001, 3.01, and 3.1, right? And then the problem asks you, this is a table describing the function f of x, right? And then the question is asking you, well, what's the limit as x approaches 1?
That's
of
you,
f of x?
right? That's you.
Where?
Like under 1, is that a 4? Or?
It's a 4, I'm sorry. Yeah, that
It's a 4?
Yes. My 4s are a little bit weird, I guess.
Oh, so it's like
Yeah, that's
the
a
dot.
4. I've never written a 4 like that.
Oh, okay.
Here. You know what? It's a 5 now.
I like it.
Just for the sake of you guys understanding, right? And also this is x equals 1. So they're like kind of different, you know, yeah, you can kind of draw that out in your head. And so if we look at the table here, right, we see that as we approach 1 from the left side, well, the y value, it's getting closer and closer to 3, right? And as we approach 1 from the right side, the y value is getting closer and closer and closer to 3. But then all of a sudden, when we look at what the function is at x equals 1, we have 5, right? And so this kind of points out the concept that with limits, we don't care whatsoever what the function is actually defined to be at this point. We just want to know what the function looks like it's going to do, right? And this actually also brings up another point, that whenever you have a limit, you actually have to check whether the limit from, or as x approaches, we're going to look at 1 right now, right? From the left side of the function is actually equal to the limit as x approaches that number from the right side of the function, right? Because if this is not true, then the limit cannot exist, right? And if you look at it graphically too, well, you can have a function that looks like, so like this, and then it has a hole here, and then it jumps all the way over here and does whatever, right? So you see that if you take the limit from the left side, it's going to be whatever that y is. If you take the limit from the right side, it's going to be whatever this is. But we can't determine what the function itself is approaching as it approaches this x, because it's doing something completely different from one side than it is from the other side. So intuitively too, and not just mathematically, we can't really have a limit at that point, right? So at a table here, we would say that from the left side, it's approaching 3. From the right side, it's approaching 3. And we do see that these are equal, so it's pretty safe to assume that the limit as x approaches 1 is equal to 3. So that's the table way to do it. We also have a bunch of algebraic ways of solving limits. So, oh, by the way, this is part 1 of the lecture, and then I'll have part 2 tomorrow during this review session. Yeah.
Smash that like button. Subscribe.
So here. Ooh. So actually, there's one more method that's not that algebraic that we have to try first, and that's whenever we have something like this. So say we have the limit as x approaches 2 of 5 divided by x minus 2, right? So here, the first thing that you should do whenever you have a limit that's algebraic like this, right, is that you plug in this x value. So when we plug this in, we have 5 divided by 2 minus 2 is 0. So 5 divided by 0, that's not defined, right? So we can't just plug it in and see what it's going to equal to. So we should try the left side limit and the right side limit to see what's actually going to happen, right? So when we check the left side limit, so the limit as x approaches 2 from the left side, well, that's the same thing as plugging in a number that's really, really close to 2, but that's a little bit smaller than 2, right? And so since it's going to be smaller than 2, and we're going to subtract 2 from it, we're going to end up with a negative number, right? So we're going to end up with the 5 divided by something that's basically 0, but it's super close to 0 and it's on the negative side, right? And that comes from the fact that this is a number that's going to be super close to 2, but a little bit less. And if you subtract a number that's greater than the number itself, you're going to get a negative number, right? And since they're so close, it's basically a 0. So from the left side, well, 5 divided by a negative super tiny number, that's basically just going to be negative infinity, right? And if we do something from the right side, if we take that same limit as x approaches 2 from the right side, by the way, that's the notation. Left side is you have a little minus, and right side you have a little plus. We have 5 divided by, well, this time it's going to be a number that's a little bit bigger than 2, but still super close to 2. So since this is greater than that, when you subtract this, you're going to end up with a positive number. But it's going to be so close to 2 that it's going to be basically a 0, but with a little plus like that to indicate that it's a positive number that's extremely close to 0. And so a regular number divided by a super tiny number, that's going to give us, and it's positive, right? That's going to give us infinity. That's a weird looking infinity. And so here we see that this, the left side is equal to negative infinity. The right side is equal to positive infinity. So that means that since they're not equal, this limit is not going to exist. It does not exist. So that's the very last method that we tried before moving on to the algebraic methods. Just plugging in numbers that are really close to each other. Okay. So we can also have, a case where we have to factor, right? So say we had the limit as x approaches 2 of x cubed minus 4x divided by x minus 2, right? So again, first thing you always try is to plug it in. If you plug in 2 over here, you get 2 cubed, which is 8, minus 4 times 2, which is 8. So 8 minus 8, you end up with 0. And then 2 minus 2, well, that's going to be 0. So just directly plugging it in, that's not going to be any avail, right? So we're going to try to factor some of it over here, because we see that there's an x in common in the numerator. So if you factor out we end up with x times x squared minus 4. And you notice too that this is a difference of squares, and you can factor this into x plus 2 and x minus 2. And then we still have that x minus 2 in the denominator, right? So you see now that this very conveniently cancels out with this, and we're just left, and again, you also have to always say that you're taking the limit, right? So this is just gonna turn into the limit as x approaches 2 of x times x plus 2. And then once you have a limit like this, that you see that there's no like dividing by 0 or anything, what you do is just plug in the number and see what value you get, right? So when you plug in 2, you get 2 times 2 plus 2, which is 2 times 4, so that's gonna be 8, right? So that's the factoring method for solving limits. Now I'll erase from the top to the bottom. Okay. So we could also have a limit, and they show up very rarely, but once they do show up, I don't want you to be like thrown off by them. Like say the limit as x approaches 2 of like pi, right? Well, pi is just a constant line, right? If you look at it as a graph, it's just a straight horizontal line. It doesn't increase or decrease, so its y value is going to change. So if you look at what it is at x equals 2, right? So if you have this is the y-axis, this is the x-axis, right? So at x equals 2, I mean, it's still going to be pi, right? So whenever you have something that doesn't have anything that's relating to x, well, then it has nothing that's relating to x. That means that the answer is just going to be pi. We don't care about what x is approaching if it's going to be a constant thing all throughout, right? So another algebraic method of doing limits is whenever you have square roots. So in this example, we're going to have the limit as x approaches 2 of the square root of square root of x. So the square root of x minus 2 divided by x minus 2. I'm sorry, this should be here. X approaches 4, and then we have x minus 4. Yeah. So over here, typically whenever we have square roots, and actually, right, first we should plug in, right? So square root of 4 is 2, minus 2 is 0, and then 4 minus 4 is 0, right? So we see that there's an issue, right? So typically whenever we see square roots, the very first thing that we should think is the conjugate of whatever the square root has, right? So if you remember conjugates from like pre-cal or any other course you learn them in, it's basically an expression with two terms, right? But instead of subtracting, you'd add, or if you're adding in the first place, then you subtract, right? So if we do what I'm about to show you here, so we'll multiply by the conjugate on the top and bottom. So this, so that's the conjugate, right? So if you do that, notice how this is just that divided by that, and a number divided by itself is just 1. So by doing this, we're actually not going to change the value of the function at all. We're just going to kind of manipulate it algebraically so that it becomes easier for us to handle, right? So this is just a difference of squares, right? So the square root of x squared, that's going to turn into just x, minus 2 times 2, which is just going to be 4. Then at the bottom here, we have x minus 4 times the square root of x minus 2. Or plus 2, I'm sorry. Yeah. So here now we see that we have an x4 or x minus 4 on the top and on the bottom that we can cancel. So we're just left with 1 over square root of x plus 2. And then again, I'm kind of doing some bad math by not rewriting the limit. But we can always keep in the back of our heads, right, that we're taking the limit. And so here, I'll just write it over here for the sake of us doing it. So if we take the limit now, we just plug it in. Well, we get 1 over square root of 4, which is 2. So 2 plus 2, 1 over 4. So whenever you see square roots, first thing you should think is conjugates. And on the AP exam, that's typically how you'll actually end up doing it. Okay, that's how you do square roots. Remember, just always multiply by the conjugate. And you're not actually changing the fraction because you're just multiplying by 1, right? So two very iconic limits that like there's some geometric proofs for them, but for the sake of time, I'm not going to just like show you the proof. So just kind of trust me, right? And you can look up the proof if you want. It's actually really interesting on Khan Academy. Sal Khan does a good job of explaining them. But if we have the limit as x approaches 0 of sine of x divided by x, well, this is going to be equal to 1. You can look up the proof for this, but it's just like a fact of the universe that this is equal to 1. And we also have the case where we have the limit as x approaches 0 of 1 minus cosine of x divided by x. And that's actually going to be equal to 0. So one thing I want you to notice about this one is that, remember, if you have 1 divided by 1 and you take the reciprocal of it, that's still going to be 1 divided by 1, and that's still going to be 1, right? So if you actually do the reciprocal of this and take the limit as x approaches 0 of x divided by sine of x, you're still going to get 1. But in this case, you're not going to get 0 if you take the reciprocal, right? Because this means that you have 0 divided by some number, and so when you do that, you divide by 0, and that's not good. And actually what the limit ends up being is infinity if you take the reciprocal, but you're not actually going to apply that anyway. So remember, these two limits are very crucial. Actually, the proof of the derivative of sine uses this and this, and so they're extremely crucial in a lot of calculus. And so to kind of get some practice with them, actually I'll save the practice for them later because they get pretty, like, to understand how to compute them, L'Hopital's rule gets really useful. So before we get into the sine of x divided by x stuff, we also have other trig limits that, like, you don't have to like memorize them, but when you get these problems, it's really useful to apply identities to figure out what they're actually going to be. Here, I wrote it wrong. So it should be, so the limit as x approaches 0 of cotangent of x times sine of x.
Please listen up for your room number. If you are in this group of rooms, teachers, you can release the students to go grab a snack. Room 101, room 102, room 103, 104, 105, 106, 107, 108, 109, 206, and 111. Only those rooms. Students, you can go grab a snack in the student lounge. Please make sure you take your money and yes. 101, 102, 103, 105, 106, 108, 109, and 206.
I guess we're all done.
Ours is kind of
Ready.
close to the end. Ours
Oh, man. Imagine they run out.
They should just set a Wait, we have to pay for pizza there. We have to
325.
pay for pizza there. Take back
charge. Okay, so here, if we look at the definition of cotangent, right? We know that actually, before we even think of doing that, when we plug in 0 into all the x's, right? We know that cotangent of 0 is undefined by its definition, and I don't want to say what the definition is because that's how you solve the problem. And then we have so an undefined number times sine of 0 is just 0. Okay. And so what the heck is that supposed to mean, right? So from this, we see that it's not really, we're not able to conclude anything from this. So we're probably gonna have to do some trig identities or algebra or something. And in this case, what actually does become helpful is trig identities. So we know that cotangent is cosine over sine, right? So if you rewrite the limit, x approaches 0 of cosine of x over sine of x times sine of x. Well, now we can see that very conveniently the two signs go away and we're just left with cosine of x, right? So we're just left with the limit as x approaches 0 of cosine of x. And then this one that's super easy to do. If you plug in 0 into cosine, well, you just get 1. So another really useful trick whenever you're computing limits is if it has trig, do try to apply some of the trigonometric identities that you know, because it ends up simplifying like this sometimes. So we also have limits when x is approaching infinity, and what these are actually called, like later on in more advanced calculus, is related growth questions. But for you guys know these as the Bobo bottom HCC, yeah, that iconic phrase, right?
There's
And
more
so-
people into this, but for us, yes.
So without really thinking about this mnemonic all that much, let's do an example, right? So say we had the limit as x approaches infinity of x squared plus 1 divided by x cubed minus x plus 3, right? So this is one of the 3 cases of the related growth question that they can give you, right? So we see that the degree of the polynomial on the numerator is less than the degree of the polynomial in the denominator, right? So we have a 2 to 3. So just kind of thinking, there's 2 ways to think about it. Either you can think about it as how they grow in relation to each other, right? So x squared is going to grow a lot slower than x cubed is, right? Like say you plug in just 3 into this. So 3 squared is going to be 9, but then 3 cubed is 27. So you see how they grow significantly faster, or this one grows significantly faster than this one. So if you think about it, as you go to infinity, well, infinity squared is going to be a lot smaller than infinity cubed, right? So just thinking about it, you're going to divide a relatively small number, right, because it's still infinity, but a relatively small number by a relatively big number. And so dividing by a humongous number, that basically gives you 0. So without even doing any math, just thinking about it intuitively, we can see that this is going to approach 0, right? Because we're dividing by a humongous number by the time we get to infinity. What you can also do is, well, that's the right answer, so I'll leave it there, is you can divide by the polynomial of the greatest degree, right? So if you divide by x cubed and 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 divide by x cubed, well, that's going to turn into 1 over x. That's going to turn into, well, actually, before I even do that, once you plug in the infinity over here, well, we can see that the x squared divided by x cubed, well, that does turn into 1 over x. And when you plug in infinity into that, that's just going to be 0, right? So this approaches 0 over here. 1 divided by infinity cubed, that's going to approach 0. This is just going to become 1, right? Actually, I'll write it below. That way it's more easy to see. This becomes 1 over x squared, which is going to approach 0. This is just going to approach 0. So we see that we have a 0 plus 0 divided by 1 plus 0 plus 0, right? And that's actually the mathematically rigorous way to do it, but you know, it kind of helps to just think about it conceptually and how this is going to grow a lot faster than that. Another way that you can do it, and this is what I think is the easiest way, is that, oh, did not mean to erase that. There. So if you just look at each of the terms that have the greatest degree in the numerator and in the denominator, right? So if we just ignore this plus 1 and we ignore this minus x plus 3, just look at the limit as x approaches infinity of x squared divided by x cubed. Well, it becomes really easy to see here that this is just going to simplify into the limit as x approaches infinity of 1 over x, which is really easy to see that this is just going to equal 0, right? So personally, I actually like to do it this way just because it's the fastest. You just have to look at the highest degree polynomial. But I showed you the mathematically rigorous way to do it. I showed you the conceptual way to do it. And regardless of how we do it, the math is still true, right? And so math is awesome. So we could also have the case where the degree on the top is going to be bigger than the degree on the bottom, right? So thinking about it conceptually, well, this function is going to grow a lot faster than this function over here. So once we get into infinity, it's going to be a huge number divided by a relatively small number. And so this is just going to go off into infinity, right? Because it's going to be a huge number divided by a really small number. It's going to be so insignificant that it's just going to go into infinity. If you do it the mathematically rigorous way and just divide by the biggest degree, well, you're going to end up with a number over here and then 0 over here. And whenever you divide by 0, you end up with infinity, right? And so mathematically rigorously, you're going to get infinity too. And just looking at these two, right, if you take the limit as x approaches infinity of x cubed divided by x squared, well, this is just going to simplify into x. And then if you plug in infinity into x, well, that's just going to give you infinity. So regardless of how we do it, we still end up with infinity. Yeah. And this method actually becomes really useful when you end up with the third case, which is where the degrees are equal. So I'm just going to focus on that third case because you've seen already the examples of the conceptual way and the mathematically rigorous way. So just looking at the leading degree terms, right? So if we look at the limit as x approaches infinity of 3x cubed divided by x cubed, well, you see that this x cubed is just going to cancel with that x cubed, and we're just going to be left with 3. So actually, you see that regardless of what we're plugging into the x here, we end up with 3. But again, that's only true because we're ignoring this plus 1 and this minus x plus 3. But if we just look at what ultimately happens as we go to huge numbers, well, we don't really care what this plus 1 is if we're multiplying by infinity cubed. And we don't really care what this minus infinity plus 3 is if we're going to have an infinity cubed, right? So these just become really insignificant. So it's safe to do this, right? And with that, it makes it really obvious that this is just gonna be 3, right? So you see that it's just gonna be the ratio of their coefficients. So if you had 2 over here, well, this is gonna be 3 over 2. If you had 8 over here, well, that's gonna be 8 over 2, right? Or which is actually 4. So you can see that whenever you have the same degree, you just divide their coefficients, right? And that's what this says. If it's bigger on bottom, then you go to 0. That's what we saw. If it's bigger on top, then you go to infinity. And actually, there's one more case I have to show
Or
you.
negative.
Yeah, the negative, yeah. And then if you have equal degree, well, then you divide the coefficients. I forgot what the each stands for. So if you have the equal degree on the top and the bottom, you're just going to divide coefficients. And then sometimes they can kind of be tricky with these problems and like involve negatives and all over the place. But if you just boil it down to that method where you just get the leading degree of each of the top and the bottom, right? So say we had, let's see, the limit as x approaches negative infinity of x cubed plus 2x minus 4 divided by x squared minus 4x. Yeah. So when we try doing this one, we can just ignore all the insignificant terms because these aren't going to matter once we get into the infinity, right? So we're just left with the limit as x approaches infinity of x cubed divided by x squared, right? And so negative, right? So looking at this, well, when we plug in the infinity into the top, a negative number cubed, that's still going to be a negative number, right? If we plug in the negative into the one on the bottom, well, negative squared is going to give us a positive number. So we know that it's going to be a negative number divided by a positive number. So we know for sure our final answer is going to have to be negative, right? And then just you can kind of ignore the negative now and just look at the limit as x approaches infinity. Just kind of simplify this a little bit. It turns into x. When we plug in infinity into x, well, you get the infinity. And then we have to remember the sign that we came up with over here. So ultimately, the answer is going to be negative infinity. Yeah. So yeah, whenever they give you an infinity, a negative, and they can also put it here or here, you always have to take into account what's going to happen with it. So always think about that negative. Okay. So then, typically, if you were just learning limits for the first time, they wouldn't teach you this right now because you'd have to know derivatives. But when we look at L'Hopital's rule, right? So say we have the limit as x approaches some number, that's just some arbitrary number, of a function divided by another function, right? So if when we plug in this number into this function and this function, and we get something that is equal to 0 divided by 0, or infinity divided by infinity, regardless of what the sign is.
I'm gonna teach the students now. So like allow them to go by.
Anybody want to go to buy the snacks can go to the student room.
Oh my gosh.